So at the very least, people are not asleep, which is very important, right? So I had the slide already, but I mean, it's already been said where I did my PhD. I did my bachelor's degree in India, in Jadavpur University. Also in computer science and engineering, I was the fifth um, batch to graduate with that degree in any university in India. So it was early days for computer science and engineering at that time. Um, and yeah, the University of Illinois at Urbana-Champaign, and in addition to Alberta and the University of Tokyo, are places I've been a student at. One of the interesting things, so I like to tell stories, and if nothing else, you'll hear a lot of stories from me in this talk. So when I was doing my my PhD, I was at the University of Illinois for half a year. At that time, a fellow computer science student who sat in the building next to mine. So my building was the Beckman Institute, and the building next to mine was called the National Center for Supercomputing Applications. So this guy in that building wrote the world's first web browser. I often ask my students to name it. Well, I won't give you that quiz, but you can always Google it. It's a thing called Mosaic. So Mosaic was the world's first web browser. It eventually got commercialized as a browser called Netscape, which was, for those of us who are old enough to remember it, was the browser to use before Internet Explorer took over. And that, of course, got supplanted by Google Chrome and so on. We know that story. So that's my story. Now, a little bit about my lab. So my lab is located in this building. We're on the second floor in the corner. And as Dr. Tan's introduction just said, we've worked with a whole bunch of companies and continue to do so. Off late, a lot of our work is defense related. So the Government Department of Defense Science and Technology Group, or DSTG, funds a lot of our research, but also Data 61, which is the other federal government entity that is in charge of doing national level research. BAE Systems is a defense contractor, a major company that's involved in building defense hardware such as frigates and other kinds of ships and so on. So we've worked with them, and we work with a few other companies, Lockheed Martin and so on, off and on as well. A lot of our work is also clinical informatics. So we work very closely with the radiation oncology group, both in our local hospital and in other hospitals in the Sydney area, but also in places as far afield as the Netherlands, where we have worked with the University of Maastricht Radiation Oncology Clinic. It's called MASTRO. We've also worked with Samsung, IBM Research, Xerox Research, and several other such companies. So that's a little bit about my research lab. So my agenda is to get you all interested in AI. So nowadays, interestingly, AI is very much a hot topic in the news and so on. But whenever people say AI, they use another pair of letters in conjunction and they say AI ML. So that's the combo that's popular right now. I am very skeptical that is the combo that will eventually deliver value. So you will probably see not much of ML or machine learning in what I talk about, because I think that, the core of AI is very interesting in itself, and we don't have to rely on, currently trendy things like deep learning and so on to make ourselves relevant. In fact, we do a lot of deep learning work in our lab, but that's not what gets me very excited. So if you think about the prehistory of AI, the roots of AI lie in mathematics and philosophy. And if you look at ancient civilizations, the Indian civilization, Greek civilization, the Egyptian civilization, various East Asian civilizations, that's where the maths and philosophy happened. That forms the core of what we call AI nowadays. In fact, that forms the core of what we call computer science nowadays. But more recently, as in the 1800s, there was this guy in the UK called Charles Babbage, who is famously credited for having built the first computing machine. Actually, there's some debate about whether they have existed for a much longer period of time, but let that be aside. So Charles Babbage is a major name in the last 200 years, and a major name again in the last 100 years is Alan Turing. As some of you know, Alan Turing was one of the code breakers at Bletchley Park, which was a manor house in the British countryside where the British government was trying to break the German wartime encryption codes. And Alan Turing, there have been movies made about him, right? Some of you might have seen these movies. Um, was the original guy who, at least in recent history, said in a paper, I propose to consider the question, can machines think? Um, and so the paper was called Computing Machinery and Intelligence, and he started by saying, can machines think? Can we make machines think? And of course, uh, in his own way, he made some progress towards making machines think. Um, and so it is that the what's informally called the Nobel Prize in Computer Science is called the Turing Award, and there is a very famous Turing test that we will talk about, and some of you probably know about it already. But even more recently, so a good 10 years after Alan Turing, guy called Herbert Simon and his colleague Alan Newell, over the Christmas break, said that we wanted to invent a thinking machine, and they claimed that they did. This was in the winter of 1955-56. And so that was an interesting claim, which was eventually supported by a conference that was, well, not a conference so much as a think tank working group that was convened at Dartmouth College in the US. But before that, a little bit about Herbert Simon. So Herbert Simon is the guy on the left. He's the only computer scientist who's actually won a Nobel Prize. But the Nobel Prize he's won is for economics and not computer science. But interestingly, the kind of economics he's talked about that won him the Nobel is in fact very relevant to AI, and is heavily used in the branch of AI which looks at multi-agent systems. His colleague Alan Newell, the second from left, is famous for having argued that we should build and describe things at the knowledge level, as opposed to the code level or the machine level. We should describe things much more declaratively at a much higher level of abstraction, and that's what he called the knowledge level. There are two other major names, and then they'll show up in the next slide, but I will talk about them first. Marvin Minsky is third from left. Marvin Minsky taught at MIT. He along with these others, were the founding fathers of AI. So Marvin Minsky was a good friend of my PhD supervisor. So I had the pleasure of having dinner with him in Cairns at the Pacific Rim AI conference in 1996 in Australia. So Marvin Minsky is famous for having started this whole business about AI with these colleagues, and also because of his work, amongst other, weirdly, on things like the confocal scanning microscope. That's an entirely different thing to computer science, entirely different to AI, but he made massive contributions in that space as well. Now, the extreme right is this guy called John McCarthy. So, John McCarthy taught at Stanford University, and he used to be a frequent visitor to the research group of my postdoc supervisor at the University of Sydney, uh, who happened to be Malaysian, by the way. His name was Professor Norman Fu. Um, so Professor Norman Fu used to invite John McCarthy, and he used to come, and I had several opportunities to interact with John McCarthy before he died. There's one interesting story I'd like to tell about John McCarthy, which is an example of good, solid mathematical thinking. So the year was 2004, and the big AI knowledge representation conference that year was happening in a ski resort called Whistler in Canada. So Whistler is about a 3-4 hour drive north of Vancouver. So we all flew into Vancouver, and then we got into a van late at night, and we were being driven to Whistler. So along the way, the van driver decided to make a stop at a very famous chain of donut shops. So this chain is called Tim Hortons. So we stopped at this donut shop, and everybody got off and had a coffee and a donut and so on. So the driver of the bus, he counted that 15 people got off the van. 15 people got off the van, and when we all came back, he counted that 15 people had got on again. And so he said, all right, we're all good because 15 got off, 15 got on, we can now proceed. John McCarthy, who was sitting in the front row of the van, said, hold on, you're right in saying that 15 got off and 15 got on, but are they the same 15? Which is a very simple observation, but it's an example of mathematical thinking. And so John McCarthy was saying that are they the same 15 that got off, that got on the van again? So I like to tell that story because it shows the power of analysis in everyday life as well. All right, so that was John McCarthy, and he was the other pioneering person in this story. So the Dartmouth Summer Research Project on Artificial Intelligence was convened with uh, um, McCarthy, Minsky, a guy called Nicholas Rochester, and a guy called Claude Shannon. Now, if any of you are electrical engineers, then you will know Shannon's theorem, which is about signal processing and the frequency at which you sample a signal, a waveform. So Shannon was famous in that space, but he was also one of the people that participated in this original project that coined the term artificial intelligence. So the study was to proceed on the basis of the conjecture that every aspect of learning, or indeed any other feature of intelligence, can in principle be so precisely described that a machine could be made to do it. That was the original premise, and that led to the original debut of the term artificial intelligence. Now, so we've talked about the pioneers. Let's talk a little bit about two schools of thought that have sort of competed for attention in AI. So the one school of thought is what is called the strong AI school of thought, and the other, the weak AI school of thought. The strong AI school of thought essentially says that artificial intelligence is about mimicking the best biological metaphor of intelligence that we know of, and that happens to be human intelligence. So we want to do inside a machine what humans can do inside their heads, which is a fine thing, except that if you look at the history of attempts to draw inspiration, to mimic biological metaphors, they haven't worked so well. So some of you might know the Greek mythological story of Icarus and Daedalus. So these guys, so the idea is that they were trying to escape off an island, so they decided to fly off the island. So they said, what flies in nature? Well, birds fly. And how do birds fly? Well, they flap their wings. So they they attached wings to their bodies, and these wings were made of wax. And of course, under the harsh Greek sun, the wax melted and the wings didn't quite work and they plummeted to their deaths. So that's the story from Greek mythology that tells us that don't always mimic the biological metaphor, because sometimes that doesn't lead to a happy outcome. Weak AI, on the other hand, says that we want to create intelligence by loosely drawing upon inspiration from nature, but by not necessarily mimicking what nature does. And so the best example, in contrast to the wax coated wings of these guys in Greek mythology, the Wright brothers said, well, let's build a flying machine with fixed wings. Now, there really isn't a biological metaphor of something with fixed wings, right? So most of what we see in nature have flapping wings, but they said fixed wings, and they built a flying machine. And as famously we know, the flying machine worked. So we have fixed wing aircraft these days, and of course we have rotary wing aircraft as well. These are the helicopters, but we have fixed wing aircraft, and they are the dominant paradigm as far as flying machines are concerned. Now, weak AI therefore says that we will draw inspiration from nature, but we will not necessarily mimic what nature does. Occasionally we might, but occasionally we might do other things. But we want to solve hard problems by drawing some modicum of inspiration from nature. In many ways, I subscribe to that second view, the weak AI view. And in many ways, the current fad with deep learning and so on is sort of attempting to mimic exactly in the last detail the kind of machinery that you would find inside the human head, which is the machinery of neural networks. So it's true that our heads are full of neurons and they form a neural network and so on. But very famously, again, Marvin Minsky, who we just talked about, Minsky and a guy called Seymour Papert wrote a book in the early 1970s, which mathematically demolished the idea of the kind of neural networks that were used at that time being of any value. So, in fact, when I was doing my PhD, people who were doing neural networks research were the poor cousins. Right? We looked at them with pity, poor guys. You're doing work on something that's already been discredited. But these days, thanks to the Toronto, he doggedly stuck to the idea that neural networks could deliver value, and he came up with this idea of deep learning, which companies have latched onto, and they're publicizing it. And yes, they do deliver value, but there are issues. We'll talk about them later. So let me see. Let me talk a little bit about some major AI milestones. Perhaps the most important milestone was something that happened at Stanford University in 1965. So this guy who's in this photo here, his name is Joshua Lederberg. He was in fact a Nobel laureate in medicine. And Joshua Lederberg was part of a team that built an expert system. It was the world's first expert system. It was called Dendral. And what he was trying to do, and that whole team was trying to do, was build a system that would take as input the molecular formula. So, C2H5OH for ethyl alcohol. So it would take as input that formula. It would take as input some mass spectroscopic data, and it would spit out a molecular structure. So that was what it did. It would compute or use knowledge to figure out the molecular structure of a chemical given its chemical formula and given some mass spectroscopic data. Now, this system was quite successful. In fact, it became fashionable for many years afterwards to write research papers and list as a co-author Dendral. Now, Dendral was no human being. It was an expert system. but it was a fashionable thing to do, to list Dendral as a co-author only because they had used Dendral for some aspect of the research that was being reported. So for many years, in fact, all the way up to the late 1990s, you could FTP into a server in Stanford and use Dendral, but then they took it down. It's no longer much in use. There are better systems around, but at that time, it was really a thing. It was a big thing. So that was a major milestone, the world's first expert system, 1965. Interestingly, I had a colleague in my department uh, who had been part of this project. And for many years afterwards, I would ask him to come to my AI classes and talk about his experiences on the Dendral project. But for some reason, he had washed his hands off the project and he never did come and give a talk to my AI class. Now, the second major expert system that was also built at Stanford University, also around 1965, was a system called Mycin. So Mycin was an expert system that did essentially two things. It diagnosed a certain class of bacterial infections and it recommended treatment for those bacterial infections. Now, the kind of bacterial infection, so it had a very narrow scope of applicability. It could only diagnose meningitis and bacteremia, two very similar kinds of acute bacterial infections, and ones which can kill. So meningitis and bacteremia can both kill unless treated early. So the whole idea was that people would use Mycin to get a quick and dirty diagnosis, get some treatment recommendations, and treat the patient according to the treatment recommendations, even as they waited for full-blown bacterial cultures, which would tell us what kind of bacteria was at play and exactly what brand of antibiotic would work in killing that kind of bacteria. So that was the premise underpinning Mycin. So Mycin was a very powerful and ultimately quite useful expert system. But the interesting thing, of course, is that Mycin had a very narrow range of applicability. Unlike your average doctor who has had 5 or 6 years of training in a variety of disciplines, including anatomy, pathology, etc., etc., Mycin only knew about these two infections and how to treat them. So that was all the knowledge it had. And arguably, the knowledge it had was also very superficial in the sense that it was built around if then rules. So, if blah, then blah kind of things. And the knowledge was at a very surface level. It didn't go into any kind of depth. But the superficial knowledge that you encoded in the form of if then rules was adequate to give you very good performance. Um, in fact, the story is that they tested Mycin against a cross section of medical practitioners in the US, and Mycin kind of outperformed 80 to 90% of those practitioners. So it was better at what it did than your average doctor, but it was only good for those narrowly defined kinds of diseases and nothing else. So ultimately, a doctor wins, but in that narrow domain, Mycin won. So that was the story with Mycin being the original medical expert system. Now, Mycin, there's another little story about it, which is that the minute you start writing down knowledge in the form of if-then rules, you worry about how do I represent the fact that I have uncertainty about these rules. I'm not 100% sure about a certain rule that I've written. If A, then B might be true in 80% of the cases, and 20% of the time it might not be true. So, what they did in Mycin was they invented their own calculus. It was the calculus of certainty factors. So, they called it certainty factors. And they built this whole thing around this brand new kind of mathematical framework that they had built for certainty factors. And in the end, they found that in fact it was flawed, that led to inconsistencies, it led to counterintuitive results. So by the time they were writing the third major expert system, also at Stanford, It was a it was a mineral prospecting expert system. They had already ditched certainty factors, and they had gone back to our mathematical foundations, and they were using probability theory. Now, probability theory has a long tradition of many millennia. So it's well developed, well understood. Lots and lots of people have studied it. So it didn't lead to the kinds of problems that certainty factors, which had been just cooked up on the fly. So probability theory was a far more reliable alternative. Now, and the story about Prospector is that it found, I think it was nickel or cadmium deposits somewhere in California, where the US Geological Survey said there was no deposit. Prospector said there was. They drilled holes and they found the Prospector was right. The US Geological Survey was wrong. So that's the story of the first three expert systems that mark the beginning of the major, the happy times with AI. The other major milestone was again late 1960s. This was the first chatbot. So a lot of you probably know about chatbots. Chatbots are really popular in industry nowadays. They're popular because chatbots can automate certain business processes which were earlier reliant on what's called BPO. Many of you know that term, right? Business process outsourcing. So, traditionally, every company would pay for a call center to be built in some cheap location, and then they would give that call center the job of handling customer queries, and you would have humans answering the phone and so on. Nowadays, a chatbot answers the phone. Now, it doesn't necessarily mean that these systems are a lot more efficient, but they certainly save companies a lot of money. And for the most part, they work well. I mean, recently, in the last several months, well, no, late last year, when we were under lockdown in Australia, um, we were doing you know click and pick up kind of grocery shopping. So you order your groceries online, and then you drive up to the shop and just pop your boot open, and somebody wearing a mask and all from the shop will come and load your groceries into your car boot for you. Now, it so happened that I had ordered one box of tea bags, and they had charged me for two. And when I called the half an hour trying to convince the chatbot not to give me a refund for two boxes of tea bags, but to only give me a refund for one box of tea bags. So they were offering to give me more money. I could have as well taken the money and scooted, but I said no, I really need to get this right. So I spent half an hour with the chatbot trying to convince it that don't refund me the cost of two boxes of tea bags, just refund me the cost of one box of tea bags. Anyway, so the original chatbot was a system called Eliza. This was named after a character from a movie, and before that, a book written by a guy called George Bernard Shaw. So the movie was called My Fair Lady. The book was called Pygmalion. And it's about the stories about a young Cockney lady who was being trained by a professor to speak proper English. She spoke with a Cockney accent. So, in any case, Eliza Doolittle was the character in the story, and the whole premise of the movie and the book is about teaching this young lady how to speak, upper class English. In any case, what this original chatbot did was a kind of psychotherapy. This kind of psychotherapy is called Rogerian psychotherapy. And the premise is that you solve a lot of your psychological problems by talking about them. So your psychotherapist makes you talk. So you go and say to the psychotherapist, things aren't going well with my studies. And so then the psychotherapist says, what's wrong with school? And keeps asking you pertinent questions to make you talk about your problems. And just the act of talking about your problems helps deal with those problems. And so it's a form of psychotherapy. Now, it was actually very simple trick programming. This whole business of the original chatbot was very simple trick programming. And in fact, it was so simple that when I first learned in second year in university, when I learned how to program in a AI programming language called Lisp, I wrote a program which was only about a page long, and I invited my fellow students in engineering, and they were mechanical engineers and civil engineers and so on. So I said, come along, come to a computer lab. And this was in the days when people didn't have their own computers. We had to go to computer labs. So I said, come along and test my system. So they talked to my system and they were hugely impressed. They turned around and said, you're a genius. How could you write such a thing? And I was, of course, laughing in my own head because it was really simple trick programming. But this was such believable trick programming that in 1968, the American Psychiatric Association, in their annual convention, they passed a resolution saying that they should lobby the US government for um, to convince the US government to shut down this kind of research, because their concern was that if this kind of research was allowed to proceed, then psychiatrists will be out of business. They would have no work. So this was that believable that psychiatrists got scared for their own jobs, when in fact the reality is that psychiatrists are trained doctors, and this system had nowhere near the knowledge that a trained doctor has. It was just trick programming. Um, so, um, to this day, this kind of business remains popular. So, there is a thing called the Lobner Prize, which is a competition held every year. What the Lobner Prize does is it subjects a chatbot to the Turing test. So, for those of you who might not know what the Turing test is, it's a simple test of AI, and it says that I'm sitting in front of a computer terminal, and in one room, the computer terminal is connected to an AI system, a chatbot. In the other room, that same computer terminal is connected to a human. And I try and sustain a conversation with both the chatbot and the human being, but I don't know which is which. And so if I can never tell, if I am never able to distinguish the human from the chatbot, then the chatbot or the AI system has passed the Turing test. Now, in actual fact, nothing ever has passed the real Turing test, but the Lobner Prize sets up the Turing test as a challenge problem every year. So this guy at the bottom of the screen is Hugh Lobner, who funds this award. I think the prize is $1 million or something, some huge amount of money, and he's an independently wealthy person who funds it. And that thing on the right hand side is Mitsuru, which was one of the winners in one of the recent editions of the Lobner Prize competition. Um, I remember the first time I taught AI at the University of Wollongong in 1997. The Lobner Prize happened to come to Sydney at that in that year, so it was quite a thing because I was talking about this, and at the same time, this competition was happening in Sydney. So that was chatbots, and these days chatbots are very much in the commercial spotlight. So there is this thing called, well, nowadays I call it enterprise automation because we're doing a lot of work with it. But originally the term was robotic process automation, or RPA. And there were companies like UiPath and Automation Anywhere. UiPath became the unicorn. They were the biggest, most well-funded startup, and it's now a huge multi-billion-dollar company. Automation Anywhere is a similar such company. It's very big. Druid is a company that makes chatbots, and its chatbots can work with UiPath's chatbots. UiPath nowadays sells the idea of hyper automation, which is some form of AI, some form of machine learning combined with the original low code, no code chatbot style functionality that they deliver. At the bottom is IBM's Case Manager, which is IBM's take on how to support what it calls knowledge intensive service processes, which means business processes which are the kind that a lawyer would execute or a surgeon would execute, which means that there is a lot of variability in what happens. So when surgery happens, then the surgeon brings to bear the surgeon's expertise in deciding on how to deal with the situation as it unravels. And likewise, a lawyer would bring to bear the lawyer's expertise and so on. So it's not business process execution in the sense that there is a fixed formula, a fixed sequence of tasks you have to execute, and it's that simple. It's actually parts of it are like business processes, and parts of it involve enormous amounts of flexibility and variability. So that's IBM's take on it. So what I nowadays call enterprise automation, and we have a fair bit of work happening with intelligent agent technology in my lab on enterprise automation. That is the idea that we're bringing to bear the power of AI to automate almost every kind of enterprise function. So in the end, you can have the idea that Gartner sells, which is called algorithmic business. 10 years before Gartner started using that term, I used to use the term algorithmic management, which was again the same idea that underpinning a lot of the stuff that happens in management is computer science, in particular with it is AI. So that's a very interesting thought that you can go to your management colleagues and say, what you guys do can be automated. In fact, we have the AI algorithms to automate most of what you do. It's interesting and it's a challenging thought because it's not a proposition that's easily or well received by the management community. All right, so going a bit further, there's AI planning. So the planning problem is the problem of computing. You're told that you are in a current state, you want to be in a certain goal state, and will take you from the here to the where you want to be. So Shaky the robot was one of the original robots that did AI planning. Now, interestingly, if you ever look at a video of Shaky in operation, it was literally, it lived up to its name. It would think, it would take one wobbly step, then it would stop and it would think for some minutes. Then it would take another wobbly step. So it was a super slow planner, but it was using the original planner that led to the whole area of AI planning, which remains today a hugely interesting and active area of research. So there was a Shaky the planner, but fast forwarding to 1999, NASA did an experiment. So it was called RAX, which stands for the Remote Agent Experiment. And what NASA was testing was the planning capabilities of intelligent agents sitting on board spacecraft. Now, NASA's proposition was that they were sending these spacecraft at that point in the late 1990s. There was a program called the Deep Space Program. So NASA was sending out a bunch of low-cost spacecraft into the outer reaches of the solar system. So for long periods of time, these smaller low-cost spacecraft would be within radio shadow of Houston, if you will. So, the old stereotype that in Houston we have a problem, right? The Apollo program and all, they all were in constant contact with ground control. And that it so happened that NASA's ground control used to be located in the city of Houston, so there would be constant communication with Houston, right? So with this program, the idea was that if your spacecraft is sitting in the radio shadow of Jupiter or Saturn, and it's quite easy to imagine how radio communication will be blocked because there's the planet in between the spacecraft and planet Earth. So during those periods of time, NASA basically said we want to be able to control the spacecraft autonomously. So the entire control of the spacecraft would be on would rely on onboard intelligent agents. So this experiment in 99 was the remote agent experiment where they artificially shut down communication with Houston and they allowed this intelligent agent to take over control of the spacecraft. They did it for 48 hours. And the interesting story is that the conclusion was that the AI worked, but human programmers failed. In fact, there was a problem, and it was a divide by zero error, the classic programmer newbie error, right? So that is what messed things up, but the AI itself worked beautifully. So that was another interesting milestone in the journey of AI, and in particular planning systems and intelligent agent systems. So now the story with intelligent agents. The guy on the top right-hand corner is Professor Mike Georgiev. He still teaches at Monash University these days. He does medical informatics. But originally he used to work for NASA, and he was famous for having built something called the PRS, the Procedural Reasoning System for the NASA Space Shuttle program. And the Australian Prime Minister Bob Hawke in the late 1980s brought him back from NASA and gave him his own institute. It was called the Australian AI Institute. It was located in Melbourne, and told him to build AI systems for Australia. One of his star recruits in the early days was the guy whose photo appears just under his. This guy's name is Anand Rao. He is these days the head of AI globally for PricewaterhouseCoopers, PwC. He had at that point just finished his PhD from the guy working with the guy who eventually became my postdoc supervisor. In fact, he left a year before I joined. So my postdoc supervisor was this Malaysian professor called Norman Fu. So Anand Rao did his PhD with Professor Norman Fu, and he went and joined the Australian AI Institute. And between Georgiev and Rao, they proposed a thing called the BDI agent architecture. That stands for Belief, Desire, Intention Agent Architecture, which became incredibly influential, and it remains influential. And to this day, we are still building defense applications, all kinds of interesting applications of BDI agent systems. One of the early systems that was built using the BDI agent architecture was a system called Oasis. It was an air traffic control system, and hence this photo here. So they decided to target one of the hardest problems ever. So air traffic control, as you might well imagine, is a very, very hard problem. And for the most part, it relies on human input. I mean, there is the whole business of scheduling takeoffs, scheduling landings, making sure that your aircraft are taking off on the right flight paths and not colliding with each other, handling emergencies, clearing out flight paths if a aircraft declares an emergency and has to land very quickly, and so on and so forth. So all this stuff that is done by a human air traffic controller. The idea was that they would build a intelligent agent-based system using the BDI agent architecture to essentially solve that problem. So they built Oasis, and they tested it using parallel data feeds from the air traffic control at Sydney's International Airport. So their original target customer was Sydney's Kingsford Smith International Airport. So the parallel data feed experiment showed that it performed as well, if not better, than the human air traffic controllers. So then there were high hopes that maybe Sydney will buy this system. But did Sydney buy the system? Well, it didn't. Why didn't it? Because if, we can ask ourselves, are we going to be comfortable flying into an airport where they tell us that there is no human air traffic controller guiding your aircraft in? It's a AI system that's guiding you in. It would make us deeply uncomfortable, and that's just human nature. It's human psychology. No running away from it. So it didn't make a sale, but it was an incredibly influential system, and it remains influential to this day. So these days, of course, we are working with BDI agent systems on problems relating to multi-agent coordination. So this is a drone swarm, and in fact, drone swarms are incredibly important in a lot of applications, bushfire response, but also national defense, national security type situations as well. Some of you might have seen a movie on Netflix called Angel Has Fallen, where there is one of the early scenes is about a drone swarm that's launched from the back of a van, and these drones show amazing coordination abilities. But these are suicidal drones; they're kamikaze drones, so they land on things or people and blow up. But they also have computer vision and all kinds of other capabilities built into them. So that's the future of a lot of things, including defense technology. So um, drones and drone coordination, drone swarms, and so on are hot topics, and we are working in that space as well. Something else that's interesting to note is the idea of a challenge problem that was originally invented by a well-known scientist from Sony Research Labs in Japan. So he set up this challenge, which he called the RoboCup challenge. And the challenge was that in 50 years' time, a robot soccer team will defeat the world champion human soccer team. So that was the challenge he posed, and that led to a whole international competition for robotic soccer, but also for software robot, so intelligent agent soccer. So we used to be active in the late 1990s in the software robot space because we don't work with hardware robots. Well, that's a lot of stuff that mechatronics people do, but we don't do that stuff. So in 1999, I sent 4 of my students to Stockholm for the RoboCup 99 competition, and we did pretty well. We were ranked 9th out of a field of 64 teams, which was very good work for about 5 months of effort. But eventually, of course, this whole thing became a bit less interesting for us because they found that there were some world champion teams like Tsinghua University in Beijing was a world champion team, but they would do unrealistic things like we know that humanly it's impossible to dribble a soccer ball with at the back of your feet, right? You can only dribble in the front, not with the back, because you can't see what's happening at the back. But their agents would dribble at the back, and so things of that sort. So they made the rules more human, hardware oriented kind of rules, and so we lost interest, and we didn't do it very much of it after the late 1990s. But it continues to this day. This whole RoboCup challenge is still a thing. So that's another example of where agent technology has been going. And by the way, the soccer domain remains a very interesting domain in which to understand teamwork. So the one thing that you know for a fact is that no amount of detailed pre-canned, pre-compiled behavior execution will help, because the range of possible scenarios you might have to handle is far too big. Also, no amount of machine learning is going to help because, again, you can't anticipate all possible situations. So, much like an actual human soccer team, you have to do a lot of your reasoning and a lot of your coordination on the fly. And these are not easy problems to solve. So, even today, we routinely refer to the soccer domain for inspiration for hard problems in multi agent coordination. Now, multi-agent systems are also used in a lot of settings where there is real industry application involved. So one of the things we built again, about 20 years ago was a truck dispatch system. So truck dispatch is a mining problem. It's a problem with open pit mining. And it's about deciding which dump truck should go to which shovel to load up on rock, right? So it could be overburdened rock, or it could be iron ore or coal or whatever it is you're mining. Without going into the details, that kind of problem is again ultimately a multi-agent coordination problem, and some very interesting things can be done. In particular, our solution in this case was to use agent-based auctions, which is where AI meets economics. So there's the theory of auctions in economics, which can translate to the theory of auctions in electronic marketplaces where agents are buyers and sellers. And that's what we used in developing this solution. This was for a specific company that was a supplier for coal mines in the Hunter Valley in New South Wales. Another little story worth being aware of is the story of Prolog and the Japanese fifth generation project. So, fifth generation computing or fifth generation programming is this idea. We've been through generations of programming languages, like first generation languages, like Fortran, which was the first high level programming language. Fifth generation was this idea that you don't have to write a procedure for solving a problem. In writing a program, all you have to do is state what the problem is. So this was the premise of the Prolog programming language. It was originally developed at the University of Marseille in France in the 1970s, but then it took off in Japan. So the Japanese Ministry of International Trade and Industry, MITI, invested several $billions in the early 1990s in building a whole suite of computing applications around the idea that all computing will be fifth generation computing of the kind that Prolog does. Now, one of the things for those of you who have not programmed in Prolog is interesting to note is that when you write a Prolog program, you don't write a procedure like you do in any other programming language, C, C Sharp, C++, Java, name it, Python, whatever, you write procedures. In Prolog, you simply define the problem to solve. And that definition is something you write in logic. So the proposition is very compelling that the mere act of defining the problem in logic is the act of solving the problem. Why is that so? Because Prolog and the whole fifth generation computing idea says that all problem solving at its heart is logic theorem proving. And so there is a universal logic theorem proving procedure, and that procedure can solve any problem. So as long as you can write a definition of the problem in logic, that procedure will solve it for you. So one of the things I would show as an example when I would teach Prolog is, you could do a little experiment. Write a program for sorting a list of numbers in your favorite procedural programming language and then write it in Prolog. Your favorite procedural programming language will require about a page and a bit of code. Prolog requires 2 lines of code. Why does it require two lines of code? Because the code for sorting a list of numbers is merely a definition in logic of what a sorted list of numbers looks like. That's all it is. And that's the program. So the act of problem solving equals the act of problem definition in logic. That's very powerful, right? I mean, it means that a lot of hard work that people do and this huge multi-trillion dollar industry globally in writing code goes out through the window because all that you have to do is define your problem and off you go. Except, of course, that defining a problem in logic is not accessible to most people. So people who do AI can define a problem in logic very easily, but say that to an average programmer that you have to write stuff in logic and they'll run for the hills because they're scared of maths. So that fear of maths has led to the failure of the fifth generation computing project. So the Japanese invested billions of dollars in the fifth generation computing project. At that time, I remember my PhD supervisor used to get a lot of funding from the Japanese fifth generation computing project, and then he did a sabbatical at the University of Tokyo, and I joined him for a part of his sabbatical at the University of Tokyo, all built around this fifth generation computing project. In fact, later on, when I joined the University of Wollongong, there was a thing called the Japanese Advanced Institute for Advanced IT, which was the institute that provided funding for the fifth generation computing project. They provided me funding as well, and we did a lot of interesting things. But in the end, it didn't take off. In the end, the reality was that the average IT person is not mathematical, and the whole premise of the fifth generation computing idea is that you must be capable of writing your problem definitions in logic, and logic scares far too many people. So that's the little story about fifth generation computing, which is worth noting, being aware of, and so on. Now let's talk about the other strand of research that is hugely interesting, which is the idea of game playing. So the lab where I did my PhD, the AI lab at the University of Alberta, is in fact very famous for its game playing, so much so that the Google DeepMind division nowadays has its headquarters in Edmonton, Canada, to leverage the expertise that can be found at the University of Alberta in AI game playing. So I'll start the story. So there was a long history of people who had done interesting research. The more recent player in that space is the guy on the left. His name is Jonathan Schaefer. So Jonathan Schaefer, I know him well. He, at the time I was doing my PhD, he was a young assistant professor, and he wrote the first, well, what became the world champion in checkers or draft, whatever you choose to call it. So checkers was a game where the world champion for many, many years was an American professor of mathematics from Florida. His name was Marion Tinsley. And he's the guy on the right hand side. The older gent on the right hand side is Marion Tinsley. For about 30 years, he had been the world champion in checkers. Now, Jonathan Schaefer challenged him to a tournament in London. At that time, the top hardware maker was Silicon Graphics, so they sponsored the tournament, and it was basically a checkers tournament. And so in that tournament, Marion Tinsley lost. He lost. He went home heartbroken. Then there was a repeat tournament, and he lost again. Then, of course, the story is that he probably was so heartbroken, having been world champion for 30 straight years, is that he fell sick and died. We all felt sorry for him, but yeah, that's what going head to head with the computer does to you. So now, what was the deal with checkers? With checkers, if anybody has any hope of beating the computer, you have to beat at that time, I'm talking about the technology in the early 1990s, you would have to beat the system in the first half of the game, because up to the first half, up to the halfway point in the game, the game was actually a real game, in the sense that there was game tree search, which is an AI technique for any kind of adversarial setting, like chess, like checkers, like Go, and so on. So in all these kinds of settings, you do game tree search. And so this Chinook system also did game tree search up to the halfway point. From the halfway point, the game of checkers was a solved problem, which is to say, all you had to do was to look up a table and say that my board looks like this, what is the right move to make here? And the table will tell you exactly what the right move is. And if you execute the sequence of moves that the table tells you, that's it, you win. So checkers was one of those, it's an easier problem than chess. In chess, you can't do this even today. You can't look up a table and the table will tell you exactly what move to make. But in checkers, being a simpler game, it is possible to do that sort of thing. And Chinook did it and it became the world champion. And I mean world champion. No human or machine could beat it. So that was the story of Chinook. Since then, that group has also done very interesting work on games of imperfect information, probabilistic games, things like poker and bridge and so on and so forth. But I won't go there now. There's a long and complex story there. Now, in the late 1990s, I was teaching my first class on AI at the University of Wollongong, and at the same time, there was a championship happening again in London, which was chess. So the guy you see on the slide here is a guy called Garry Kasparov. These days he's a Russian politician, but at that time he was the world chess champion. Now, Kasparov was playing against a chess computer fielded by IBM Research. So that chess computer was called Deep Blue. Now, the reason it's called Deep Blue is because IBM used to be called Big Blue because, for many decades, IBM employees used to almost had a corporate uniform which was blue suits. So IBM was called Big Blue, and so this chess computer was called Deep Blue. But the history of that group that built Deep Blue is that they had originally built a machine, a chess playing machine, and I mark my words, it's a machine in the sense that it's not just algorithms, but it's hardware optimized for executing those algorithms at CMU, at Carnegie Mellon University. But originally that group came from my AI lab at the University of Alberta. So from Alberta, they went to Carnegie Mellon, and from Carnegie Mellon, they were picked up by IBM Research, and they became the Deep Blue team, and they played Kasparov. Now, Kasparov lost that tournament. And Kasparov complained bitterly because what he said was that normally a chess player builds a mental model of the opponent. And so that mental model is really important in influencing a player's decisions. But for Kasparov, he said, it felt like I was playing a new opponent every day. And the reason it felt like that was because of something called an evaluation function, a heuristic evaluation function, which is fundamental to any game playing algorithm, which was being tweaked with every day. So the IBM team had a few chess grandmasters on their own payroll, and they were tweaking that function. Between matches, every evening, they would tweak that function. And so the next morning, Kasparov would face effectively a whole new player. So any mental model he had built, which was what good chess players normally do, they build a model of the opponent, was useless. And so this guy complained bitterly. But anyway, so this was the big story in the late 1990s with computer game playing. And then, of course, the big story was 2016, right? So AlphaGo, which most of you have heard of. The game was Go. Lee Sedol, the South Korean world champion, was challenged by Google DeepMind. So there is this Taiwanese guy on the left hand side who worked for DeepMind, who was making the moves. He wasn't actually a real Go player. He was simply reflecting on the Go board whatever AlphaGo was computing as the best move to make. And of course, we know that the story is that Lee Sedol lost. So that's interesting because adversarial reasoning has made great strides, and adversarial reasoning is fundamental to a lot of things. The most obvious ones are obviously, if I'm dealing with a real adversary. So if I'm in a defense or national security kind of application, then I'm saying, my adversary is clearly my enemy, whoever it is. And I want to anticipate the adversary's moves and build a strategy which works, which stands up to all kinds of bad things the adversary might try to do to me. So that sort of thinking applies in very obvious cases, but it also applies in everyday things like business process execution, where you can say, it's a game of me versus the environment, and I'm going to assume the environment is doing the worst it can to me. That's the worst case that can happen. And if I build a strategy which is resilient and robust against, adversarial moves by the environment, then I'm in a good place. So adversarial reasoning is enormously important in all kinds of settings, and so it is also important in playing the game of Go, chess, and you name it. Another area where AI is very heavily used is in industrial optimization. These are some screenshots from a system we built again about 20 years ago for our local steel plant, and one of the downstream entities from the steel plant was a company called BHP Building Products. They built roofing material and fencing material from steel, and this was a production scheduling system. And one of the big application areas where AI can make a huge difference to people's bottom lines is in optimization, solving industrial optimization problems. One of which was the truck dispatch problem I talked about earlier, but this was one where we were doing industrial scheduling. There's also multi-agent optimization, where you say that not all of the optimization knowledge is available in a centralized repository. Some of it will remain distributed, and some of it with minimal information revelation, how can we coordinate the solutions of the agents to get some kind of an optimal solution? That's a very interesting area, very hard problem. There was a lot of work on it until about 10 years ago, and then people sort of said this is too hard and went away. But I think there's lots of interesting things that can be done in that space. A brief mention of the semantic web, which is another application of AI. This is AI where we are doing semantic markup of web content. Semantic markup is, if you will, knowledge-based markup. So HTML gives you the opportunity for doing visual markup of content. Semantic markup is where you're doing knowledge-based markup of content. So if you look at my homepage, you'll see, the fact that I am a professor of computer science. Now, semantic markup will tell you that a professor is a university academic, and as such, a professor or probably also has a PhD degree. So these are things that you find out by virtue of semantic markup, and you can do a lot of sophisticated reasoning about web content by virtue of the semantic markup. And so this was the semantic web. This idea was introduced at the International Joint Conference on AI in the year 2001 in Seattle, and I was at that session where this was introduced. It was very exciting. At that time, it was very exciting. Lots of people thought that, HTML will go out of fashion and it will be replaced by these semantic markup languages. It didn't quite happen that way, but it might well happen in the future. So it's not that the story isn't over yet. Much like, e-commerce in the early 2000s People thought this was a thing, but then it kind of fizzled out, and then it kind of came back in a very funny way. But now it's part of our everyday lives, right? So it's the same thing with semantic web. I think it'll come back at some point in some form or the other. Um, Something I want to talk about as a word of warning. So when I was an undergrad, AI was flying high. This was the mid to late 1980s. I would go to our university library and I would open uh, the top magazines in our professional space. So IEEE Computer, ACM Communications, and there'd be page after page of job ads for AI engineers. That's what they call them, knowledge engineers or AI engineers. And every company that you knew about, Ford Motor Company, Rockwell, NASA, name it, they were all hiring hundreds, if not thousands of such people. This was because people had hyped up AI. And so the whole hype said that, you can solve all kinds of hard problems by simply using rule-based expert systems. By the time it was the late 80s, early 90s, industry figured out that that wasn't really the case. You couldn't solve all problems by writing down very large knowledge bases of rules. And so when industry goes into something, they go in as a herd. So they operate like a herd. And when they ditch something, they also ditch like a herd. So en masse industry sort of said, okay, we're giving up on AI. AI is a bad idea. We don't want to do AI. So they fired their thousands of AI engineers. At the time I was finishing my PhD in AI, every job ad for an academic position in the US or Canada said, all areas of computer science welcome except AI. So it was a bad time for somebody like me with a PhD in AI to be looking for a job. Well, fortunately, Australia at that time didn't do what the rest of the world was doing. So Australia was still welcoming people with AI PhDs. In fact, not just me, but a whole bunch of my colleagues in Australia today all came around the same time. I call ourselves the AI refugees because nobody else in the world would take us, but Australia would. So we all came to Australia because Australian universities provided a welcoming home for AI expertise. And so we all ended up here at that point in time. Of course, then slowly AI made a comeback, it clawed back, first with web crawlers, search engines, and then with the agent technology. And of course, once the Googles and Facebooks of the world figured out deep learning and vision and so on, then they hyped it to the heavens and created this whole thing around. Sometimes people even call it deep technologies, whatever that means. I'm very skeptical about this thing because you know right now we are being told that deep learning and similar machine learning techniques are the solution to all of life's problems. They're not. And when industry figures that out, they're going to ditch AI all over again, and we'll go through another AI winter, which is why I'm telling the story that this has happened in the past and it can happen again. We have to be aware of the fact that we should always focus on the modest ways in which we can deliver value and not hype things up unnecessarily. So, as you can see in this little talk, it's a random thing I picked off the web. Some people are saying that maybe the next AI winter is approaching again. Now, even if you look at some of the work that is happening in deep learning and so on, we do a lot of it in our lab. So, I'll give you an example of what we have done recently. We have built a system that learns from open source project data on how to predict whether a given open source project is going to go over time or not. Now, at the heart of this prediction machinery is a deep learner. And that time it was TensorFlow that we used to build it. But then it wasn't just a deep learner. It was because just the deep learning machinery alone didn't give us sufficient predictive capability. So it was deep learning plus some other machine learning modules, stacked on top of each other. And if you ask me, why did you do it that way? All I can say is, well, it worked. And that's why we wrote a paper. We got some good results and we wrote a paper about it, because by trial and error, one combination of machine learning, older style machine learning modules stacked on top of deep learning gave us good predictive accuracy. And so we wrote a paper. And what does the paper say ultimately? It says that if you have the misfortune of running into the same data set that we ran into in a dark alley at night, at least you know that the techniques we used will help you for that data set. But it's because it works only for that data set and no other. So if you look at what advance did we make in human knowledge and science, the answer is not much. It's a very modest advance. But because we are dealing with the currently trendy topic, it's easy to get published in the top journals and so on. So there's a lot of that happening. So for those of you who are saying this guy is supposed to be talking about AI and he's not breathing a word about machine learning, it's because I'm somewhat skeptical. I think that machine learning has its place and it's useful, it's worthwhile doing, but it isn't the solution to all problems. I mean, so some years back we were recruiting a new lecturer in AI, and we said in the interview panel, design for us a 13-week class on AI. So this one guy says, in the first week I will teach deep learning, in the second week I will teach applications of deep learning, in the third week I will provide case studies on deep learning, and the fourth week. And so it was deep learning all the way through 13 weeks. And I said, have you heard of other parts of AI? Like there's other kinds of things that people do, reasoning, diagnosis, agent systems, adversarial reasoning, and so on. And the guy said, no, all I know is deep learning. So there is this problem that we often nowadays are confusing AI with deep learning. Deep learning is just one of a massive collection of very useful AI techniques. I'm not saying deep learning is useless, but it has to be used judiciously and it should not be overhyped or oversold. So now the last few things I'm going to talk about are a few comments about the role of data and so on. So in 2008, the Wired magazine ran an article which was called The End of Theory. And basically, so there was a guy called Chris Anderson who's very famous. So he was making the point that data is coming at such a high speed that it makes the whole idea of teaching somebody the theoretical framework for science obsolete. So it's almost like saying that if I am a lecturer in physics or chemistry or biology, I'll say at the start of a 2-hour lecture, I'll say I need to give you a warning that what I'm going to teach you might be obsolete by the time the lecture is over. Now, that's a very funny concept, right? But it's a thing that Chris Anderson argued was happening, that we were getting data at such high speeds and big data and so on and so forth, that it made the whole idea of a textbook obsolete. In fact, there was a workshop that some of my colleagues in the Netherlands went to, where they actually explicitly asked that question: is the idea of a textbook now obsolete? Are we going to generate textbooks at the press of a computer button because the theory will be generated on the fly? Now, of course, this is again hype, because in actual fact, we're not changing the scientific principles that inform our understanding of nature at that speed at all. If anything, we are the only place where our understanding is evolving somewhat rapidly is in medicine, where we knew so little about how the body works, how biological systems work, that as we get more data, our understanding is growing quite rapidly, and that's a good thing. So there was that end of theory argument. But then I am claiming that there is also an end of data argument. So that revolves around this idea of alpha zero. So those of you who haven't heard of alpha zero, so the idea was that AlphaGo was trained on actual game playing data. So there was a machine learning component that was trained using a long history of past Go games. They used a Go champion who was living in France to collect a vast data set of past Go games, and they trained the machine learning module and so on. But then they realized that doing it that way was incredibly slow. So their simple solution was to say, have an AlphaGo system play an AlphaGo system. Now suddenly there is no need for data because the computer based game playing machinery is a proxy for the data. And that says something really interesting for us, because a lot of times people sit and say, oh, I can't get the data is so hard to access, it's so hard to collect, people won't give me access to their data, and so on and so forth. This throws the whole data argument out through the window. It says, well, use a computer based simulation as a proxy for data. And that's a very powerful idea. Now, of course, in some settings, it's hard to do. I mean, what's a computer based proxy for human medical data? Nothing, right? So you actually need people to fall sick, you need some people to get cured and some people to die to collect the data sets from which you learn lessons, right? But in other cases, a computer simulation can be just as effective as a large data set. And that is what AlphaZero teaches us. Something else that's interesting is something that was pointed out to me by a Polish colleague of mine. He said, we're learning from big data, right? So if we had confined ourselves to learning from big data, then what we would be driving today would be very efficient, very sophisticated horse-drawn carriages. Because big data says that you cannot depart from the precedent of past data. Whatever you learn, whatever lessons you conclude, will be based on what you've used and what has generated the past data sets. And if all you've ever used is a horse-drawn carriage, your data sets will teach you lessons about better and better horse-drawn carriages. But what about the internal combustion engine? That's an example of where you depart from past precedent, where you depart from data and you make a quantum leap, what we call innovation, right? And big data analysis does not support innovation, because big data analysis forces you to stay within the bounds of what past data reveals. So that's an interesting thought, that if we had stuck to big data analysis alone, we'd be just driving better and better horse-drawn carriages. Now, something else that's interesting. So this is um, a, a, a story that tells us that sometimes, data-driven insights can come from unlikely sources. So this story involves an actual episode in World War II. So this is 1943. The Allies had invaded the south of Italy and they were moving up north. They already occupied a place called Bari, which had a major harbor. So the American Navy was, um, sitting in Bari Harbor in full force. There are lots of ships sitting there. And the German Luftwaffe, they launched an airborne attack on Bari Harbor, and they blew up a bunch of American ships. Now, when these ships blew up, as it turned out, some of these ships contained a banned chemical weapon. In particular, it was mustard gas. Mustard gas was a chemical weapon that was used in World War I, and then people said it's a bad idea, and people signed international treaties and conventions banning the use of these things. But the Americans in secret had actually shipped vast quantities of mustard gas to Europe, and those ships carrying mustard gas were sitting in Bari Harbor when they were bombed by the Luftwaffe. Now, what happened was that several, close to 1,000 American servicemen, mainly US Navy personnel, were affected by the mustard gas that blew up. Now, what the Americans did was they hushed up the whole story and they flew these 700-800 US Navy people back to the US. And what they found was that the mustard gas had killed the bone marrow of these people. Now that's a bad thing, right? So the bone marrow was killed. And so what happens is that your body ceases to have the ability to produce more blood, because our red blood cells are created in the bone marrow, as are, I think, the white blood cells as well. Now, curiously, that was a solution that doctors had been searching for. Why? Because they were trying to find a means for battling hematological cancers, things like leukemia, where the bone marrow cells start proliferating, and then we get these white blood cells and red blood cells in the wrong numbers and wrong proportions. And for the life of them, they could not figure out how they could chemically stop the bone marrow from producing these cells. And suddenly, with these injured Navy people who had been shipped in from Italy, they found that all these people had their bone marrows killed. So mustard gas was a solution. So mustard gas was the original cancer treating chemotherapy agent. And how did we find that out? Because of a airborne attack on the harbor, which had ships carrying mustard gas. So sometimes, so what is this saying to us? That sometimes we get data-driven insights from the most unlikely sources. And it's not planned and it's not designed as a scientific experiment. It just opportunistically presents itself to us. And we should always be prepared to leverage those opportunities. I'm sort of running out of time. I'm going to briefly mention that we are also doing work on using optimization as an AI solution to climate change. There's lots of interesting applications. So yeah, I'll take questions now. So before I take questions, I'll also add that we have lots of interesting projects going on. We are constantly looking for PhD students and research collaborators. So if anybody is interested in anything I've talked about, and indeed many things I haven't talked about, please do contact us, because we have PhD opportunities, scholarships, research assistantships, and just generally we're open to research collaboration as well. So please do get in touch. All right, so that's my story, and I'll stop now.
Awesome. Thank you for the wonderful insights and the sharing, Prof. Yeah, so we're going to open the floor to any questions. I'm sure most of you have questions to ask. But then again, knowing students, right? Some of you all might be a bit scared to ask certain questions here. So
yes,
you can.
There is a story that I bite. Anybody who asks a question gets bitten by me. So.
Yeah, I'm sure it's just a gentle nibble. Yeah, but you can either ask the questions, you can unmute yourself and ask questions, or you can type in the chat. Or if you are really shy, you can request for Prof's email, and I'm sure he's more than happy to answer your questions there. Yeah, so I'm going to open the floor to anyone and everyone who has any questions. Don't everybody jump in at once. Okay. There's a Yao here who asked, Prof, I wonder, how did you start your journey in the AI field? So that's a very interesting question.
So there's an interesting story behind that. So I got interested in AI when I was in